Good evening, everyone. So I'm discussing about question number 7.10 of the gravitational chapter of NCERT. So here question they are asking if in the following two exercise choose the correct answer among the given ones. The gravitational intensity at the center of the hemispherical sail of a uniform mass density has the direction indicated by the narrow is maximum, which has maximum when it is at the center. So let us see here. This is your part. This part we are talking about the question we are talking about at this center. Which direction? In the direction of A, in the direction of B, or in the direction of C, the maximum field intensity is there. So let us assume, let us see here. If this hemispherical object is not a hemispherical sail, it is complete spherical sail. So what will happen? From every side at the center, every side there will be a force acting due to each and every part of the mass. So what will happen? What will happen? Net force will be zero. Net force will be zero. But in this case, what happens here? In the no masses is at the above. So the only mass is below only. So we need to find the below. So below, let us consider in this direction there is a force, in this direction there is a force, in this direction there is a force, in this direction there is force. So as all these are symmetry, so the net force will act downward. So which is the maximum force which will act as a downward, because if there is a force acting in this direction, so what will happen? What will happen? It will have a two component. This is component in this direction and component in this direction. So both will cancel out. Both will cancel out. But at the same time, when the component of this force is in downward direction, so again at the same time the component of this force is also downward direction. So the net force is in downward direction. Okay, direction. So hence our answer for this question will be downward, that is C. So the correct answer is C. I hope you have understood this question. Now the same type of question, but there is a situation is different. Now the situation is that for the above problem, if the direction of the gravitational intensity of at an arbitrary point P is indicated by the arrow D, E, F, G, so we need to find the maximum force. So let us consider this is an arbitrary point. So arbitrary point, we generally what we will think that the mass on this side will be more and the mass in this side is less. So basically our force should be in this, net force should act on this direction, but the correct answer will be at a E. Now let us try to explain you why this E happens. Let us consider here, since this is your hemispherical part, okay, and now let us consider this is a point. Now from this point we have two mass. Let us take one mass first of all. Let us take at this angle. Let us take this as a vertical line. So this I have drawn as an angle theta. Again I have taken a same angle theta. Now I have also drawn one angle d theta. So there also I have drawn the angle d theta. So which is at a small, which is also known as a small angle. So this is a small angle d theta. Okay. Now see here, this is since hemispherical sail, so it has some amount of mass. It has also some amount of mass. Okay, let us consider the density. Rho is the density of the spherical shape. Density of spherical sail, areal density. Okay, so the mass is equal to what? So the mass, if there is a small mass, that is, consider this as a dm1 and consider it as a dm2. So the small mass dm, mass that is equal to dm1, can be written as area into density, that is pi into radius. So the radius, let us consider this as a radius r1. So this is your r1 whole square into sigma. Okay. At the same time, if we talk about the dm2, so dm2 can be written as pi into r2 whole square into sigma. Okay. So we have got this mass. Now let us assume that we will assume this as a arc. So when we talk about this arc, so can we take for a small angle d theta, can we take here, this is your dr2 and this is your r2, or r2, small r2 also, we can also write here small r2. Oh, sorry, again I have to draw, because again I have to draw, for sorry for that. See, let us consider a spherical tail like this, and we have taken a point P which is at this distance, which is at this distance. Now from this distance, uh, this is a vertical line, this is a vertical line. Now from with the reference to this vertical line, we are taking out, we are taking one radius r1 and another radius or another length r2. Okay. Now we can draw this again. We have already taken angle theta. Here also we have taken theta. We can also take here d theta, as well as here also we can take a d theta. Okay. So what happens? It takes a small area. Let us consider the small area has mass dm2, and here also it has taken this small area having a mass dm1. Now let us consider sigma as the mass density. So dm1 can be written as area a1 into sigma. Area is your pi into r. Since this the r length is your r, so pi into r1 whole square into sigma. Here also for dm2 we can also write here a2 into sigma, that is equal to pi into r2 square into sigma. Now if I will consider this pole as a triangle, because it is approximately a small angle theta. So if we consider this as a d theta, and this as a radius r2, and this length is d r2. Okay, uh, this is your dr2. Okay, and here the area pi r square can be considered as dr2 square. Here also dr1 square. Sorry for that. This is your dr1 square, because it is your dr1 length. I've considered this circle as having a dr1 length, and this circle is having a length of dr2. Okay. Now from this triangle, what we can consider, tan theta is equal to dr2 by r2. So dr2 can be considered as a tan theta into r2. Now let us consider the force. Let us consider a force, the force between this mass. Suppose this is mass m and this is mass d m2. So the force will be how much? The force formula of the force is equal to g into m small m into d m2 divided by the length is how much? Length is your r square. But we have seen that dr2 is proportional to r2, because tan theta will be common for this area and this area. Okay. Why? Because we have assumed that both are inclined at a tan theta only. So we can say that dm2 is proportional to r square. So can we write here g into small m into r2 square by r2 square. So finally r2 r2 got cancels. So the force is equal to gm. So at the same angle we are getting the same force. Okay. So if we are getting the same force, so what will happen? At the same time the net force will act downward. So our answer for the E answer will be E only. So net force will act on a downward. But if you see that, you will think that the most of the force will act on this direction, but that is wrong. So I have already explained you. So I hope you have understood this solution. Okay. So this is a answer. Answer for this question is 2. That is E. Now let us consider question number 7.12. A rocket is fired from the Earth toward the Sun. At what distance from the Earth's center, the gravitational force on the rocket is zero, mass of the Sun is given, Earth is also given, neglect the effect of the other planets. So let us assume that we have a Earth. So this is your Earth, and we have a Sun. So this is your Sun, and we have a let us consider a rocket at this point. At this point, the rocket is at this point, and this for this point the rocket is having at this point. So at this point net force will be zero. We can consider this that the rocket, the gravitational force is zero at this point. Okay, gravitational force is zero. Okay, so this will only be possible when the gravitational force will only be possible when the pull due to the earth will be equal to pull due to the sun. Okay, so when will this happen? When the pull due to earth, that is force due to earth, is equal to force due to sun. And you know that this distance of the earth from the sun is given. Let us consider orbital radius of the sun of the earth is re. Let us assume that this distance of the rocket from the earth is x. So this will be how much? So this will be re minus x. I hope you have understood. Okay. Now, force due to earth is what? Let us consider force due to earth is g into mass of the earth into mass of the rocket. So let us consider mass of the rocket as mr, mass of the earth as capital Me, mass of the sun is capital M into S. So this is mr divided by x square, and this will be equal to g into mass of the sun into mass of the rocket divided by re minus x whole square. So finally this will got cancel out. This will got cancel out. So we are getting here we will get re minus x by x whole square, and this is equal to mass of the sun divided by mass of the earth. So the mass of the sun they have given as 2 into 10 power 30 kg divided by mass of the earth is how much? 6 into 10 power 24. So when we calculate this, so we will get 1 by 3 into 10 power 6. Okay. So finally, if we take a root under, so finally root under, that is re minus x by x is equal to 1 by 1.73 because the root under 3 will be 1.73 into 10 power 3. So from here we can get x. When we conclude x will be equal to 1.73 divided by 1000 plus 1.73 into RE, that is orbital radius of the Earth. So we can neglect this point because if we multiply it by 1000, if we add, so there will be no impact on too much. So the radius of the Earth is how much? 1.73. 1.73 into radius of the Earth is given as radius, not radius of the Earth, orbital radius of the Earth from the Sun is how much? So this will be 1.5 into 10 power 11 meter divided by 1000. So finally our answer will be 2.59 into 10 power 8 meter. See, because it is 1000, so 1000 will get cancelled out. So finally, x, the distance at which, this is the distance at which rocket has zero gravitational field, gravitational force. I hope you have understood all the process. Okay. Now let us discuss question number 7.13. How will you weigh the sun? The estimate its mass. The mean orbital radius of the Earth around the Sun is 1.5 into 10 power 8 kilometer. So it can be written as the mean radius, that is RE is equal to 1.5 into 10 power 11 meter. So we should take it as a standard. So how you will do this? So see here, as we know that there is a sun at the center. So there is a sun, okay, and around the sun, Earth is revolving around the sun. So this is the Earth, and it is revolving around the sun. So can we get that the force between these two is equal to how much? So the force between these two, F, is equal to G into mass of the Earth into mass of the Sun divided by orbital radius, that is RE whole square. And this force must be equal to the centripetal force. Centripetal force. And one of the famous formula for the centripetal force is equal to m omega square into R. As we know that omega is equal to 2 pi by t, omega is equal to 2 pi by t. So can we put here m into, m is the mass of the Earth into omega, that is, let us write it properly. This is mass of the Earth, this is mass of the Earth into 4 pi by t square into orbital radius of the Earth. Okay. So this is equal to G into capital mass of the Earth into mass of the Sun divided by R into E whole square. So from here, mass of the Earth, mass of the Earth got cancelled out. So finally, we will get the formula for mass of the Sun is equal to 4 pi into RE whole cube divided by G into T square. Now we need to put that each and every one's value so that we can get the perfect answer. So this is your 4 pi into, what is the orbital radius? So this is 1.5 into 10 power 11 whole cube divided by G. What is the general formula for the G? G has a value 6.67 into 10 power minus 11 into 10 power minus 11 into time period. So our Earth has a time period how much? So Earth has a time period of about 365 into 2.5 days. So can we convert it into second? So 365.25 into days. Number of days is um, one day has a 24 hours. 24 hours. So 1 hour has a 60 minute into 60 second. So finally we have to square this. So when we will square this, so we will get approximately mass of the sun as a 2 into 10 power 30 2.0 into 10 power 30 kg. So this is the final answer for the mass of the sun. So we can find mass of the sun without weighing it. I hope you have understood this. Now this is question number 7.14. Okay, this is written as the Saturn year is 2.5 times the Earth's year. So can we write here time for the Saturn is equal to 29.5 times the time of the Earth? This is the equation they have given. Another thing they have given, how far is the Saturn from the Sun if the Earth is 1.5 into 10 power 8 kilometer away from the Sun. So let us consider there is a Earth and there is a Sun and there may be a Saturn. So this is a Saturn. Okay. So the distance RE they have given. So RS we need to find. RE they have given us RE as 1.5 into 10 power 11 meter. We need to find RS. So can we use the Kepler's law? We know that Kepler's law T square is equal to T square is proportional to R cube. So can we write here T square is equal to K into R cube. So for time for a Earth is equal to whole square is equal to K into R cube, RE whole cube. We can write this. And also time for the Saturn whole square is equal to K into R orbital radius of the Saturn whole cube. Now if we divide equation 1 and 2, divide equation 1 by 2, so we will get TE by TS whole square is equal to RE by RS whole cube. So T by TS is TE by TS, TE by TS mm, is equal to 1 by 29.5 whole square, and this is equal to RE by RS whole cube. So from here we can also find RS as RS as 29.5 whole square into RE, that is 1.5 into 10 power 11 whole cube by 3. So this will be, so here we can write here 9.55 to RE. Finally, we can get RE or 1.5 into 10 power 11. From here we can also write the final answer is 1.432 into 10 power 22 meter. So this is the orbital radius of the Saturn. I hope you have understood this. Okay. Now this is an interesting question. Here we are asking a body weighs 63 Newton on the surface of the Earth. What is the gravitational force on it due to the Earth at a height equal to the half of the radius of the Earth? So, the case you need to understand that earlier, let us consider this is your Earth. Earlier, the object is at this point. An object is at a this point, and this object's distance from the center of the Earth is RE. Now, the second case, this object has been put at the distance this distance such that this radius become 1.5 RE. Okay, so we need to find the force. So as we know that force has a formula F is equal to G into M into small m by R square. So what we saw that G is constant, capital M that is mass of the earth, and small m same mass is there. So this will remain constant. So what will be vary? So force radius will be vary. So F is proportional to 1 by R square, or F is equal to K by R square, we can write here. Now F1 is equal to K by R1 whole square. This is the case 1, or this is the case where when the object is at a RE distance, that is equal to K by RE whole square. And this F1 is how much? This will is at a 63 Newton. Now we want force when it reaches to this surface, which is at a distance of 1.5 times RE, because it is at the half of the R radius. So F2 is equal to K by 1.5 into RE whole square. So K divided by 1.4 means 3 by 2. So 9 by 4 RE whole square. So K by RE whole square is 63 Newton. So here 63 divided by 9 into 4. So 9 7 0. So finally force F2 is equal to 28 Newton, which is the correct answer for this. So finally we have got force F2 as a 28 Newton. I hope you have understood this question. Thank you for watching this video. Thanks.